We have defined two different functions for a discrete random variable. We've defined the probability mass function, PMF, and we have defined the cumulative distribution function, the CDF. Now we can define the CDF for any random variable, but the PMF is only valid for discrete random variables. In this lecture, we'll have a look at the relationship between the PMF and the CDF for a discrete random variable. So here is the background, x. That's my discrete random variable. It has a probability mass function, which we denote by lowercase f. It is defined like this. The probability that the random variable will take the particular value, lowercase x. The cumulative distribution function, the CDF, on the other hand, is defined as the uppercase f function. And it's defined as the probability that the random variable x will take a value lowercase x or smaller. So we want to investigate the relationship between these two functions, lowercase f and uppercase f, for a given random variable. To do that, it's nice to have an example. So we'll do this very simple example of the sample space being alpha beta. The probability that we will pick alpha is 0.7. Probability we'll pick beta must then be 0.3. Our random variable maps alpha to 0 and it maps beta to 1. The CDF function f of x will then be equal to 1 if x is greater than or equal to 1. 0.7 if x is greater than or equal to 0 but strictly less than 1. And it's 0 if x is strictly less than 0. The PMF f of x will be equal to 0.7 if x is equal to 0, 0.3 if x is equal to 1. And we can add 0 otherwise. The functions, they look like this. I have x here, 1, 0, 1. The CDF function is 0 until we reach this one. Then it jumps to 0.7. It stays there to 1. Then it jumps to 1 and it stays there. So this is our f of x. The PMF is 0.7 here. So we'll just draw a thick blue guy here. And it's 0.3 here. And outside these values, it's 0 all the way here and here. So before I describe the relationship between these two functions, let's introduce some notation. We will define f of a number with a minus sign at the end of this number as the left-hand limit. So a here is an arbitrary real number. It's the left-hand limit, the limit when x go to a from the left of f of x, and it's equal to the probability that x is strictly less than a. In our example here above, we had, for example, f of 0 was equal to 0.7. But for a value slightly less than 0, which we denote by 0 minus, if we're slightly to the left of 0, then the capital F function is equal to 0. Similarly, we had that the f of 1, well, that's the probability that x is less than or equal to 1, that must be 1, but slightly to the left of the number 1. If I look over here, just to the left of that, then the CDF function is 0.7. And that is the probability that x is strictly less than 1, which it can only be if the experiment ends up in alpha. So with this left-hand limit definition, we can describe the relationship between them. First, you can always find the PMF from the CDF using this formula. Let's try it out. For example, f of 0 is, according to this formula, capital F of 0 minus capital F of 0 minus, just to the left of 0. And we know that this is 0.7 minus 0, which is 0.7, and that is precisely what we know it to be. F of 1 is equal to CDF evaluated at 1 minus the CDF evaluated at slightly to the left of 1, and that is 1 minus 0.7, and that is 0.3, and that is correct as well. This also works when x is not in the range. For example, f of 0.5 is f of 0.5 minus f of 0.5 minus, that is, well, if you look at the CDF at 0.5 here, it is 0.7. And slightly to the left of 0.5 here, well, it's still going to be 0.7. So 0.7, and that's 0, which makes sense because x cannot take the value 0.5. It's not hard to prove this. It simply says that the probability that x is equal to x, that's this part here, is equal to, this one is the probability that x is less than equal to x, minus, and this one is the probability that x is strictly less than x. And this must be true no matter which x we use. If I, from the probability that we are less than equal to x, subtract the probability that we're less than x, what remains must be the probability that we are at precisely x. Second, we can always get the CDF from the PMF, and we get it by summing the PMF. The sum here tells us to sum over all outcome in the range of x, where xi is less than or equal to the particular value of x for which we're trying to evaluate the CDF. So let's try out this formula. Let's see if we can figure out the CDF at x equal to 1 using this formula. First, remember that the range of our random variable x is x1 is 0 and x2 is 1. Two possible outcome, 0 and 1. According to this formula, f of 1 should be the sum of all possible outcome I, where xi is less than equal to 1, f of xi. If you look at the range, you see that both outcomes satisfy this condition. Both of them are less than equal to 1, so we need to make the sum over both outcomes. So it's f of x1 plus f of x2, which is 0.7, plus 0.3, which is 1, which we know as the correct answer. If we do f of 0, for example, same thing, summation over I, where now in this case xi is less than equal to 0, f of xi. In this case, it's only this outcome that will satisfy the condition xi less than equal to 0. So this simply becomes f of x1, which is 0.7, which we also recognize as the right answer. If you look at something like f of minus 1, well, then you're supposed to sum over all f of xi, where xi is less than equal to minus 1. The only problem is that none of them are less than equal to minus 1, so this is simply an empty sum. It doesn't contain any terms, so this must be 0.